Just waiting for a moment for it to catch up. Okay, good morning and good afternoon and good evening to wherever you are in the world, and welcome to the second day of the Reddit Robotics Showcase. I'm thrilled to have you all here. We are very excited today for our second two sessions for manipulation and legged robots. I'm now going to hand over to Michael, who is going to be our host for this session, who's going to introduce our keynote speaker. Michael, thank you very much. Take it away.
Thank you, Ollie. All right, everyone, welcome to day 2 of the Reddit Robotics Showcase. This morning, we're going to be discussing all things manipulation. So we're going to be seeing some robots that look more like traditional manipulators like you'd see in a factory, and we're going to be seeing some that look a lot more humanoid and organic. And to start us all off, I'm going to be introducing our keynote speaker, Rich Walker from Shadow Robot Company. Rich is the managing director of the Shadow Robot Company and has been working with Shadow since 1999. He is always looking for new and interesting ways to apply robotics in any number of different contexts, ranging from crucial research to mission-critical industry work. Shadow's most well-known work is the Shadow Dexterous Hand, a robotic gripper modeled after the human hand with advanced dexterity and applications in any field where human hands are currently used. Please welcome Rich Walker.
Thank you very much, Michael. So I'm just going to do the 30-second faff to get my slides up. Bear with me 2 seconds here. Robots, share. And start the presentation. Now, is that coming up nicely?
Yep, we can see it fine.
Fantastic. So thank you very much. It's Sunday afternoon here in the UK, so a bit of an unusual time for me to give a talk, but a great opportunity to reach out to a group of people interested in robotics, because I have to say that the reason I'm here now doing the job that I do is I was fascinated by robotics back when I was younger. I was a kind of geeky kid writing software on early computers before we even had networks and things. And I wanted to write AI software, this was back in the 1980s, and realized that robots were kind of the thing I wanted to be doing that on. So I started out trying to write software for robots and ended up running a team now of I think 50 people who are developing some of the most advanced applications of robot hands in the world. So this talk is loosely about what we've been doing recently, which is what we call Haptic Telerobots. On the left there, you can see one of our robot hands. This is something that is the same size and shape as your hand and has similar kind of abilities. We've yet to really crack how to get robots to use all those abilities, because the human hand is incredibly complex, incredibly capable, and programming that turns out to be a real feat. So we often use this in what's called teleoperation, where we have a human move and that tracked into the robot hand. I'll talk a little bit about that during this talk. So we set up Shadow. We came together as a team actually before 1997. We knew each other back in the 1980s and early 90s. We set up a company in 97 because we were building some interesting things, and people said to us, can we buy those from you? And we were like, I guess you can. And there's, okay, well, we'll need an actual company for the paperwork. So we set up a company, and we looked around at what we could do with that we couldn't do before that. And one thing we lucked into really was that it was possible to get government funding to do R&D and technology at the time. So we got a bit of money out of the UK government, which we used to build some of our first robot hands. Before that, we actually built bipeds. And if you were lucky enough to see the UK Science Museum's robots tour exhibition has been going around the world, you'll actually have seen our original wooden biped in there next to the Honda HRP1, their first biped. It's a nice juxtaposition, because it was actually when Honda released that we decided to stop building bipeds. We kind of looked at it and said, this is a giant Japanese megacorp putting its best engineering people onto building bipedal robots. Possibly it's not the thing that we should be focusing on doing. And then we later found out that it wasn't just that they were putting their best technical people on it, they were using their marketing budget to build bipeds, because they couldn't actually work out if there was a business case for it, but it looked like fantastic marketing. So we kind of went, okay, maybe there isn't really an opportunity there. Maybe bipeds are too difficult to do right now. What else needs doing? Because part of the reason we were doing bipeds was no one was when we started. What else needs doing? And we settled on building hands for robots because it struck us that robots needed to be able to interact with the world in the same way that humans do. They need to pick things up, they need to move things around, they need to handle the objects that you and I handle on a day-to-day basis. And all of those objects are designed with the human hand in mind. So we said, okay, that's what we're going to do. We're going to build robot hands. And this slide's actually a couple of years out of date because we're now up to 50 people. We're based in London and Madrid because Brexit. And we have sort of co-workers and colleagues in various other places around the world. And the nice thing is that we've been, because robotics is one of those truly global professions, we sell to people all over the world. In fact, it's a very rare year when we aren't mostly exporting what we do. As goes internationally to people. There's all kinds of great and fascinating people we work with. These are some of the organizations that over the years we've supplied robot hands to, or we've collaborated with on R&D projects there. So some obvious space agencies and things, but we're actually very pleased by working with the Japanese airline, ANA. You may know that there's an Avatar X Prize running at the moment, one of the X Prize Foundation competitions, and that's funded and sponsored by ANA, the airline. And the reason why they're funding an X Prize is they realized a few years ago that it would be great as an airline to move out of the very congested market, which is selling plane seats. And so they sat back and they thought, how can we change the way we think about travel? And they did at one point decide that teleportation would be a great way to change the way we think about travel, and looked at going down that route. But that's possibly a bit of a hard push, even from a company willing to take a kind of 50-year view of how do you get there. So they've ended up looking very hard at telepresence. And that's how we've ended up working with them, putting together some of the best systems we can build to allow you to be remotely present somewhere without having to physically travel. Really, really interesting idea. And some of these other organizations, I mean, OpenAI have done some fantastic work in the last few years using things like our robot hands to verify that their AI systems can in fact learn to do real world tasks. I know OpenAI have now moved off in a different direction. I'd be very interested to see what they come up with next. But I think there's still plenty that can be done with AI and robotics, and we're very excited to see how that plays out over the next few years. So this is actually some clips from the work that OpenAI did. You can see here that they've got the robot hand manipulating an object in hand, reorienting the cube. And a later version of this system was actually able to solve the Rubik's Cube in hand by moving it. Now, I can occasionally solve a Rubik's Cube with two hands. Doing it with one hand, it's just like, yeah, I don't have the manual dexterity to do that as far as I can tell. So seeing a robot actually controlled to do that, even though we thought it might be possible from a practical point of view, we'd never seen it happen. So it's just really, really impressive to do that. They're not actually using things like the sense of touch here. This is very much about optical tracking of the cube and motion tracking of the fingertips. You'll see the markers there, OptiTrack tracking markers to localize things accurately. But still, the robot was able to learn to do this really impressive manipulation task because it does have the same abilities as a human. And you can see there's 2 movements at the wrist, and you've got 5 movements on the thumb and 4 on the fingers. And the little finger can bend up a little bit more as well. So good range of movement there. So what we've been doing with that is we've been saying, okay, how can we apply a human-like hand with robots? Writing software, fantastic. If you're an AI guru, great, go ahead, do that. But if you're not, how do you get the robot to do something? And so we've got very, very excited interest in telerobotics, and telerobotics with a sense of touch, tactile sensing, because that's kind of the human sense of touch is a really important part of how we interact with the world, how we do things, and how we are able to do manipulation as well as we do. So the video here, Mike on the right there is not wearing a VR headset. The picture at the top is someone with a VR headset on. On the right, Mike is wearing a blindfold. As he moves his hand across, he's wearing one of the gloves from Haptics. That gives him a sense of touch back. You can see on the robot hand there, those little teal light green discs at the fingertips. Those are tactile sensors from a company called SynTouch that give us an amazing sense of touch here. And when Mike feels that sense of touch, he closes the hand. It's a standard commercial robot arm. The other interesting thing about this is that this was in Tokyo in January 2019, at ANA's headquarters building. We went over there, we took the system and basically put it together as an integrated system for the first time in their offices and got it up and running. So you see there, we've got a sense of touch. We're tracking the human hand movement. We can feel things. We can do things there. So the human is providing the intelligence, and then the robot hardware and the glove hardware is giving the human the ability to understand what they're doing. We then kind of went a bit further out with this. We took it to San Francisco. Well, we took the gloves to San Francisco and left the robot in London. And we had some people from Wired trying it there. People often ask us how we did the networking, what super network connections did we use to get a high-speed, low-latency link from San Francisco to London? And the answer is we used a 4G phone in the Wired office and normal fiber internet in our office, and we didn't need to do anything else to get the connectivity, because it turns out the internet's basically good enough for this stuff now. Actually, 160 millisecond latency between London and San Francisco over a normal network connection can be done, works quite well. We actually had much more latency over the video. The video was running about half a second latency, but if you have a sense of touch, that's not so bad, because you can actually feel the object when you reach it and then not crash into it, which is what you do with the latency being the other way around. So what's the tactile sensing doing in this? Why is it important to have these touch sensors? Well, this is something about the fingertip that we're using. It's actually really hard to make things like the human finger. There are 8 different types of touch sensing cells in the human body. 4 of them happen on the hairy regions of your skin, and 4 of them happen on the non-hairy regions of your skin. And they measure some very different things. So one of them, for example, is optimized for 7 Hertz vibrations. And why that? Probably because that's the kind of frequency of vibration you get when something slips through your fingers under gravity. Seems to be about what's happening there. And then others measure different things, and they measure them over quite wide areas or quite narrow areas. So a lot of the work that Syntouch did was essentially to work out how to build a fingertip that was like a human fingertip in the data that it produced. Might be built in a very different mechanical principle. And in fact, what they've used is sort of fluids being deformed with a solid core and electrodes, so they can measure the differences between them. But that means they can measure not just where is the fingertip being touched, which you can do with the same kind of touch sensing that gets used on a phone screen, but you can also measure things like shear and slip. So you can tell how the forces are being applied to it, which is kind of important for handling things. And then you can use that to understand what sort of thing you're touching, and even more cleverly, you can do things like measure the temperature of the thing that you're touching and the heat flow, and that can tell you whether it's metal or wood or plastic. Vibration is really, really interesting. And one of the things that I didn't realize until we started doing this is that actually your fingerprints, part of the reason you have them is they make that vibration much louder. Effectively, they're an amplifier for it. And that means it's much easier for you to feel and understand things from that vibration. So this is the kind of thing that we then have to try and replicate back into the robot technology to get the same kind of movement properties. Temperature is quite cute here, because essentially when you touch something, your sense of whether it's warm or cold is not to do with the temperature of the object, it's to do with the flow of heat in and out of your fingers. And that's something that you use to tell the difference between different things. So you can see from the graph there some very different characteristics of different materials when you first touch them. And that's something that we try and pull out on we try and pull that data out so the robot has it. We can't yet render that data back to the human. There aren't any good ways to provide similar heating and cooling at the fingertips of the person. If anyone listening happens to have a good way to do fingertip heating and cooling or something that simulates it, please drop me a line, because we're interested in working out ways we can get that to work. And I should say perhaps that as a company, we are very collaborative. We work with lots of other companies, small and large, and we're always interested in ways we can take the technology that we're using and link in technology other people are using to solve bigger problems or harder problems. So yeah, Syntouch did quite a lot of work with these fingertips, and they came up with a 13-dimensional way of characterizing the sense of touch of an object that actually allows them to discriminate things really well. It's a really, really nice system, very, very powerful. And they've actually turned this now into a tool for evaluating the quality of materials. So if you buy an expensive car, the materials used for providing the finishes in it are supposed to feel like they're expensive materials. As a manufacturer, you might not want to use natural expensive materials because sourcing them, quality assurance and so on, you might want to manufacture material, but you want it to feel like the premium material you would have done. So how do you characterize that and test that? And actually giving robots a sense of touch has meant that we can now use that to do things like tell the difference between real and fake leather and make fake leathers that feel as good as real leathers. So it's kind of an interesting diversion. So for the robot, what does touch do? Well, it connects humans with the world. It's the way we understand things. It's the way we understand what we're interacting with and how we're interacting with it. If you do things without touch, then stuff gets hard. The pictures on the right there are the Willow Garage PR2 robot being used to do teleoperated picking objects up. And the thing there is that it's a strong enough gripper that it's quite likely to damage things as it picks it up. And it didn't have the understanding to say, oh, actually, I'm squeezing this object too hard. I don't need to do that. You can build that understanding in other ways. I know how big the thing is. I've moved my joints to that position. I've moved my joints further in than that. I must be applying force. But that's not perhaps as good as actually having the sense of touch that's there. And there's some very interesting work that was done with amputees, looking at how they use touch or don't use touch. So the person there, Jesse Sullivan, they're testing him there with a prosthesis that they're adding a sense of touch back to it. And what's really interesting is that very much changes the way that you use something like a prosthetic. If you can tell when it's touching something, you don't have to look at it as much. If you can't feel what you're doing with your hands, you tend to focus on them and look at them and concentrate. And that means that you can't be aware of other things. You can't be thinking about the bigger picture of what's doing. You have to concentrate on it. But the sense of touch gives you that feedback loop that means that you can then use something else. So you can do something else with the rest of your brain rather than having to concentrate on the basics of handling. Robots can do things really, really well. Rubik's Cubes keep coming up, and I apologize for that. There we have one of the world's fastest Rubik's Cube solver on the top, doing it with their hands, with their fingers, and they're using a general purpose tool, the human hand, to solve the Rubik's Cube. At the bottom, a classic robotics approach to solving everything like that is you build a machine that does everything exactly right. And there's a machine, it does everything exactly right, and it can solve a Rubik's Cube incredibly quickly. However, if you then gave that a different object and said, now do something else with it, the robot couldn't do that. So it can do one task incredibly well, but it can't do a generality of tasks. The human can be more general, which means less efficiency at any specific task, but much more ability to do a wide range of things. And really doing that without a sense of touch will be incredibly difficult. I don't know if there are any professional Rubik's Cube solvers who have impaired touch. I do know there's been some research on how touch works, as actually things get really difficult really quickly without it. So what we've got to is this point where we can now give the robot a sense of touch, we can give the human a sense of the feedback from that, we can understand what's happening, and that means we can actually do interactions like the ones on the right there. That's kind of the first step to doing a remote medical inspection, as it were, remote medical intervention. And we are doing a little bit of work with the Mayo Clinic, looking at how you can work to do general practice medicine remotely. You know, can you have a look at a patient? Can you press something, poke something, squeeze something, feel them, do the interaction with them necessary? And this sense of touch is kind of key to doing that. But the other thing here is that this is a very human-like robot at this point. It's got the sorts of movement that you make. It's moving in the same way because it's being controlled by a person to do that. So there we're kind of exploiting the benefits of having a human in the loop, but we also have the benefits of having the kind of robotics technology. So what can we do with that? Difficult, dirty, and dangerous, the 3Ds. They're all the bits that robots are exciting in. Dull tasks are quite good for robotics. There's lots and lots of applications where we take things that humans do at the moment that are fairly tedious jobs and we have robots do them. But where we're seeing the kind of real line of interest for this sort of technology is in the areas where it's, for whatever reason, hard to get a human there. Maybe it's because it's a sterile environment and a human has to be dressed up in the appropriate, the clean, sterile conditions to go in there. Maybe it's because it's a dangerous environment. The risk profile is high, undersea or working in nuclear. Or maybe it's just that the place is a long way away. We're talking to some companies who have workplaces that are hundreds or thousands of meters long. And if you want to get someone from one end to the other of them, that takes quite a long time. So just getting a skilled expert from one end of the building to the other, maybe a Tele robot has advantages for that. There's also opportunities when you start to bring intelligence and autonomy into these things, where the robot can do 90% of the task and the human can do the 10% that the robot system can't do yet. So the robot could, for example, take the front panel off, and then the human could put a probe in and take some readings, do some tests on a piece of machinery, something like that, where the robot can do the bits that you don't need necessarily, or the bits that you have now automated, but the bits that you can't automate yet, the humans can still do those. And we're now looking at doing that with kind of fairly, what to humans are very simple tasks. Pick up a cable and plug it in. Okay, so this is a USB cable. So we all know there are 3 ways to plug a USB cable in: the wrong way, and the way that finally works. The robot here has a slight advantage that at least we've tried the 2 wrong ways first, and we're going for the 3rd right way. But doing this with a robot hand is quite impressive technically, because it's something that's proved very, very hard to do. These connectors were not designed to be inserted by a machine. They can be, but it's just not easy for a machine to do it. So getting this to be done with a human doing it remotely has proved really, really interesting. And this is effectively a nice proxy for a wide range of tasks where you want the human to do something at a distance because you want to perform maybe even a very, very simple intervention, turn the thing off and on again physically at the switch, but it can't be done remotely. And so you need to be able to have this kind of ability. Over in sort of pharma manufacturing, there's a lot of lab work. There's again a lot of things that are skilled tasks that are done in person, and maybe they don't need to be. Maybe they're just very repetitive tasks. So a lot of pharma lab work. I mean, this kind of thing, if you're doing it at scale, you'd be using a microplate well array system that would have hundreds or thousands of wells, and you'd have machines to do that all day, every day. But when it comes to doing 1 or 2 or 3 things, or a process with a lot of distinct steps in it that need to be done, you're going to be using these kind of tools and equipment. And here, the Telerobot can do that, and then B, that can then be programmed and taught and repeated. But also it means that you've got the opportunity to, we were talking to some people the other day, and they said one of their biggest problems is they have an entire lab full of machines that do things with cell cultures and so on. And then Saturday afternoon, something runs out. And so somebody has to go into the office on a Saturday and refill a bottle. Simple as that. And they can't do that without sending a person physically there. Absolutely ruins someone's weekend. Such a pain, such a first world problem. But actually for them, it's a real issue, because it does mean that their staff are having to be on call to go and fix a machine. And boy, it would be so much nicer to do it with this sort of technology. Other areas we've got a lot of interest from, and we're talking to a lot of people in nuclear. That picture on the left there is a promo shot from a British nuclear site. This is them showing what it's like at the moment, and this is kind of best practice. And you've got someone there on a step ladder in a suit with a breathing apparatus on. He's wearing, you can't see them in the picture, but he's wearing Wellington boots that are taped to the suit. He's reaching in there through those glove ports, operating a piece of machinery on the other side of that. Wearing a suit like that for more than 3 hours a day or 3 hours at a time is basically forbidden under UK health and safety operating rules, because you sweat really badly. It's a really physically uncomfortable environment to be in. And in fact, the instructions for wearing them is when you finish the shift, the first thing you do is sit down at a cooling station and hydrate. And you are just fed a mixture of kind of Gatorade and Lucozade and water to get your hydration levels back up again. And really, you shouldn't do more than 2 or 3 hours of that a day. And that's just kind of unpleasant. And it kind of sucks that we still have to ask people to do that on a regular daily basis. You know, there's people who are doing this every day, and there'll be 2 of them doing it as well, one doing the task and one there as the assistant. So on the right, you can just see us doing something simple with the Telerobot. That is the kind of tasks that people do in these circumstances, cleaning up metal swarf in the bottom of a glove box where things have been machined. That metal swarf is probably something fairly toxic. You clean it up, you put it in a storage container. At the moment, that is done exactly with a brush and dustpan. The UK nuclear industry is getting very excited by handheld battery operated vacuum cleaners, because those are actually a big step forward for them in terms of doing tasks like this. And we're thinking, okay, well, we can use those, we can put other tools in, we can have the robots do these tasks instead. So we also have a lot of people who do interesting R&D with our products. In fact, that's been our kind of key space for many, many years. Our first robot hands went to the University of Bielefeld in Germany, and we've always had good relationships with people doing really interesting cutting edge R&D. You can see here the National University of Singapore doing some work on making fingertips, making skin, making sensing for robots, and they're using our robot hands because actually that means that you can then do really interesting tasks. As a company, we both provide hardware for researchers, and we work with them in collaborative projects. We like doing these kind of international collaborations, national or international collaborations, basically because you get to meet really, really interesting technical people who are doing really cool stuff and help them do that better, faster, and solving bigger problems. So that's something we're always really excited by. So I've tried to keep this fairly short because it's a sort of quick overview. We think this sense of touch is a really, really important concept for robotics. It's something that people have been developing sensors for many, many years, but when you look at what gets used on robots, you find still they have quite a simple approach to touch. With Telerobot and robot hands, we have the opportunity to have much more complex sensors of touch there. Then we run into the second problem, which is how do we use that data to give it back to the human so the human can use it? We've seen that people can interpret that data to make interesting insights into the things they're touching, but actually turning that into something that a human can use, rendering it back to the human fingertip, is still really, really challenging. And we think we're just at the first stages of that journey now. So with things like the Haptic gloves, we get a sense of feedback on the human, but it's not really enough yet to do these tasks as well as we'd like to do them. So if you're interested in the problems of touch, problems of tactile understanding, tactile sensation, haptic rendering, then please do come and talk to us later on now. And I think I've got time now for a few questions, if there's anything from the audience. Thank you.
All right, thank you so much, Rich. That was a really fascinating presentation. So we're still waiting on people to post their questions on the YouTube page, but for now, I'll start us off. It seems like this is a very kind of actuator intensive hand, which would lead to, I guess, a very expensive product. Do you guys have anything in the works to kind of bring the complexity or the cost down a bit to make it more accessible to people trying to buy hundreds of these for production?
Yeah. We go around the loop on the kind of essentially production manufacturing space every couple of years, and our normal answer ends up being, if you tell us what you're trying to do, then we can build you the right hand for doing that. That may not be a fully anthropomorphic, fully human-like robot hand. If all you want to do is pick up cans all day, then you probably want a suction gripper or a magnetic coupling gripper or a 2-jaw gripper, 3-jaw gripper, much simpler product, and there are plenty of those out there. Where we specialize is essentially saying, well, let's go all the way. Let's give this robot full generality, full dexterity, and therefore put a hand like that on. And you're right, there are 20 Maxon motors in every single one of those hands. That sort of thing starts adding up really, really quickly, but that does give it this kind of the full flexibility and capability that the human hand has. Yeah.
All right, thank you so much.
Can I ask a question quickly?
Sure.
Again, thank you very much, Rich, for your participation. Can I ask, so you were saying that you do partnerships with universities where you provide the physical hand itself. Obviously, those hands are, like you said, a cost barrier there. Is there anything like a simulation or a virtual version? Is there anything that in that kind of way that could enable people to work on or experience in some way a simplified even version of your kind of hands?
I'm glad you asked that. So I have the interesting journey that I'm an ex-programmer. And as the business person running the company, I sometimes get asked, what was the kind of most important business decision you ever made? I say, almost difficult. And I tend to answer that by saying, it was the day I obsoleted every line of code I'd ever written for the company. This was basically when we discovered ROS. We had built a really nice, I say it's really nice because I wrote it, real-time robot control architecture, ran on RT Linux. It was RTAI. It was absolutely fantastic. Great thing. We were the only people using it, so it was difficult to maintain and support. And then ROS comes along and we're like, oh yeah, this is better. Let's start using it. And ROS, of course, has Gazebo in it, which meant that very, very quickly we moved to having a virtual model of the hand that you could program and control and operate. And people went, oh, that's nice. Oh, so we can do stuff with this. If you've used Gazebo, you'll know its physics is great for doing small cars driving around but it's not so good for doing contact interaction. So we've moved on since then, and we have simulations in several of the other robot simulation architectures. The Construct has one. There's one in Mujoko. The Mujoko one is very, very physics accurate, and it's what OpenAI were using for a lot of their physics exploration work in what they were doing in their control. So these simulations are there. They're linked on the Shadow website. If you download the ROS packages with our hands in, you should see the tools there for getting up to speed with that. And then you can run simulations, you can build models, and we do a lot of that kind of stuff in-house ourselves because our team are distributed. Our lead teleop engineer is actually over in Snowdonia, and he's trying to run robots in London. He spends a lot of time doing that virtually as well as doing it remotely. So it's an important tool in our armory. Yeah.
Okay, thank you, fantastic. Michael, do you have any questions from YouTube?
Yeah, we have one question from YouTube that asks, what are any of the disadvantages to using the tactile sensors?
So tactile sensors carry a cost. There's a significant benefit, which is you get the touch there. But as you can see on that video, maybe the fingertips of the robot are not the same size as human fingertips, because the tactile sensor is actually, there's quite a lot of complexity in there. There's quite a lot of mechanism. And that's something we found to be a real challenge, is having something that, because the less human sized the fingertip is, the less easy it is to perform a dexterous task. So really the kind of sweet spot for a touch sensor is it gives you enough data to provide those insights, but it doesn't take up any more space than the human fingertip would itself. And that's proved a real challenge in building and deploying these kind of touch sensors. Is just getting not just getting the technology right, but getting the integration of that technology into a form factor that we can use.
Okay, thank you. Another question was, how much benefit is there to having the same tactile feedback from the fingertips, but spread throughout the hand? You know, so mounting sensors all throughout the lower fingers and palm versus just the fingertips.
So it's interesting, we did a bit of work with an engineering company who had a task they wanted to do remotely, and I can't go into details about the task annoyingly, but when they tried using our system, the first thing they noticed was that we didn't have anything on the palm. So they were picking up a tool and going, wait, I can't feel it. I can't tell that I've got the tool. I need to be able to feel the pressure of the tool on my palm to be able to do the task. And we're like, oh, okay, right. So we're now looking at ways to put touch sensing on the palm to give it that kind of insight. On these, the distal, middle, proximal phalanges, the middle and proximal phalanges, you do need some kind of touch sensing on there, and that is something that we've had various versions of working. Equally, it's something where if people have got an interesting mechanism for doing it, we're always curious to look at those and see other ways to add touch sensing.
Okay. One thing that springs to mind, which I imagine you're already aware of, is the Toyota Robotics Institute have the Ponyo bubble gripper, which is like a silicon bubble with a camera inside that can measure a pattern printed on the inside. That seems like the kind of thing that looks good on a palm of a robot. I don't know what that means.
There are a lot of sensors exploiting the shift to optical and back, as it were. We know how to get computer vision to do lots and lots of things. So using computer vision to make touch sensing is a kind of really obvious shortcut. What's interesting about the Biotax sensors we're using here from SynTouch is they are completely not thinking in a computer vision way. So whilst they have an array, you don't read it out in a way that you would if you were thinking of a camera looking at something. So it's a different way of looking at the problem, a different way of sensing the problem, and it has certain advantages and certain disadvantages. Yeah.
Okay, thank you. Michael, there's also one question in the Zoom chat.
Yep, I've got it. One question related to kind of your point earlier is how small can you make these tactile sensors? Someone was wondering about surgical robots where the loss of touch is kind of a big challenge there, you know, kind of a mission critical thing.
Absolutely. There's been a lot of work on essentially trying to provide a sense of touch that mimics what the human finger does for surgeons. So in the UK, we've had people at King's College and at Queen Mary and at UCL all working on this. Kasper Althofer, Helga Werdemann, for example, and they've been looking at ways to replicate things like what you do when you do palpation and building things using optical sensing, fiber optic cable reflective sensors to kind of produce things that are very, very small and provide that kind of localized touch contact sensing. I don't think any of these have yet got to the point where they're being deployed in the surgical field, but I know that's the area where the area of research is pointing. And it is a real problem. If you've ever been lucky enough to try the Da Vinci system, it's fantastic because it has incredibly good stereo viewing and quite an intuitive manipulation control. It's really easy to do things that would seem to be quite difficult, like tying a knot in something. But because you don't have that sense of touch, it's still slightly more limited than you'd like in terms of getting the full kind of flexibility that the human would have. On the other hand, if you actually had your fingertips in there, your fingertips would be a lot bigger than those Da Vinci tools. So it's a trade-off. You get the benefit of the micro manipulator, but you get the disadvantage of currently it's hard to provide a sense of touch.
Okay, thank you. And then another question from YouTube: are the sensors applicable for like a leg or a foot sensor for people trying to use, like a bipedal robot remotely?
They have been used in. So this particular sensor, I don't think they've made in that configuration, but I know there's a lot of skin sensor technologies that get used like that, put on the feet of robots. Typically, those are things like the capacitive touch sensing, where you're squeezing essentially a capacitor, or something like force sensing resistors, which actually come in form factors that are very suitable for putting under the foot. One advantage of the foot is it's a lot bigger, so you have a lot more space to play with. One disadvantage is you're dealing with constant loading. By definition, a bipedal robot is putting all of its weight on its feet, and that means that your sensor has to be a lot more mechanically robust. And one thing that we often find when we're talking to people who are developing new types of sensors is that they haven't understood the difference between something that works a couple of hundred times on the bench and something that works when you're pressing it with tools and equipment all day, every day. And that durability is even more critical when you're putting the full weight of a robot on it and moving over rough surfaces, rough terrain. Yeah.
Great. Okay. And then I guess last question, just on a more general level, what is kind of the future for these hands? What are your next steps? Where do you see the hands kind of going and evolving into?
So we very much like to be building the best robot hands in the world. That's kind of if you ask us what our core purpose is, it's building awesome robots that make people's working lives better, and we do that by building the best robot hands in the world. This hand is pretty good, but it could be better. So we're always looking at things like new actuator technologies, new sensing technologies, ways to make the system more rugged, more reliable, and ways to build versions of it that are more appropriate for specific domains. So for example, if you were using this in a pharmaceutical sterile lab, you'd have to get the robot to be sterile. That means you're going to have to make it differently. That means you're going to have to use different materials, different choices about the way you screen it, and so on. If you're working in nuclear, you're going to want something that will tolerate high doses of radiation. This probably can't. We haven't tested it up to those kind of levels, and we were frankly unlikely to, because it's an expensive hobby testing things for radiation sensitivity. So we'd be looking to build something in that domain which would have better, more applicability. But generally, we've spent 20 years evolving this hand, and the physical appearance of it hasn't changed very much in that time, because we're limited to the size and shape of the human hand. It's always going to, if it's going to have human dexterity, it's always going to look very much like a human hand, because that's what gives it that dexterity.
Great. And we actually did get one more quick question from YouTube, which is the motors used for these hands are still quite large. Are there any important, I guess, improvements in motor technology that you guys are looking into for this, or that you're looking forward to?
Motor technologies is kind of one of those areas where there's probably still a lot to squeeze out of it, but it's not our field of expertise. So what we tend to do is we say, well, we could build our own actuators. And in fact, we used to do that. We did a lot of work with pneumatic muscles, and the first 15 years of building our robots were all done with pneumatic actuation. And we realized there that we were playing catch up with 150 years of motor development. And there are a lot of very clever people who have done a lot of work making electric motors as frankly wonderful as they are today. So our approach at the moment is we buy these fantastic Maxon RE13s and RE16s and just use those because honestly, they hit a sweet spot of capability. If someone came along with something else that hit that sweet spot of capability, we'd give it a go pretty much straight away.
Excellent. Well, thank you very much for coming and talking to us today. This has been
pleasure.
Really fascinating, and we've been very happy to have you. So with that, as Rich invited, if you have any other questions or if you know about thermocoupling effects with human fingertips, please reach out to him. And we have a little bit of time before our next presentation, which will start in about 20 minutes. So we'll take a quick break and we will see you all back then.
Thank you.
Hi, Dan. Can you hear me okay?
I can. Hi, Michael.
Great. It's good to hear. Good to see that microphone and video is working for you. After the next presenter, we will give you a chance to do a screen share test.
Okay.
Hi, Dan. Can you hear me okay?
I can. Different quality, but yes.
Great.
Sorry, you can also try now, just be aware that we are live. But if you want to try just sharing the screen now, if you want to do that test now, you can do that as well.
Okay, we can see that fine.
Cool. Not meeting controls. Well, sure. Stop share.
Please mute your microphone as well until we're ready to start again.
Yeah, Patrick, go ahead and unmute.
Check anything? Hello? Hello? Check. Okay, I am unmuted. Trying to figure out how to make it louder.
Yep, we've got you now.
Yeah, we hear.
We can hear you fine now.
Okay, is it good?
Yep.
Okay, great. Thank you.
No worries.
I'll go ahead and get set up here.
Hi, John. Just to say that we're now live. Chris will be hosting, so he'll take over in a moment. Sorry, not Chris. Michael will be hosting, so he'll take over in a moment.
Okay, yeah, I figured I'd get set up.
Okay, we'll go ahead and come back from our break and get started. Our first presentation back from the break is going to be on Continuum Robots with John Till. So everyone, welcome John Till. Take it away.
All right, thanks for the introduction, Michael. My name is John Till, and I'll be talking about Continuum Robots. I think the best way to explain about Continuum Robots is with a video. So the defining characteristic of Continuum Robots is that you've got the flexible links here. In this case, we have some nitinol rods, which are thin enough to bend. And the rods are fed through a base plate here. And you have these linear actuators, which are effectively controlling the lengths of the rods beyond the base plate. So the control of 6 rods results in 6 degrees of freedom control of the end effector. And this robot is actually a pretty cool design with hollow rods with tendons fed through, and it can control a capstan pulley to move a gripper at the end. So the design is actually inspired from the Stuart Go platform, which is something that you'll see occasionally on the subreddit. So here's an example here of a post by Alanis Morissette controlling a ball on a Stuart Go platform. So these platforms, they're used a lot in flight simulators and advanced lifts with extra articulation. Let's see. Fighting the PowerPoint a bit here. So that design inspires the Continuum version, which you can see here. So some of the potential upsides of the Continuum version are that the compliance makes it good for working in fragile environments where you would be worried about the robot impacting the environment, and also for safe operation with human operators. You have the inherent compliance where you couldn't possibly have the robot exert too much force. So here's a better view of the design. You can see the actuator back here that's actually controlling the robot. And then a second actuator pack controlling the tendons for the gripper. And these motors are being controlled by an Arduino Mega. And it's connected to a PC, which is actually doing the hard kinematics work and sending commands. So interestingly enough, the mathematics of the rods have been solved for a long time. Kirchhoff was the first to derive the differential equations for elastic rods. And then the Khosrow brothers came up with more descriptive equations around the start of the 20th century. But recently there's been interest to numerically solve systems making use of elastic rods. And for this robot, we're actually solving a boundary value problem to figure out the right joint inputs for the robot. Although I won't go into the details for this talk. So although the robot is quasi-static, we can also do dynamic modeling of the rods and robots. So this is a cantilevered rod being hit near the base with a sudden impulse, and the simulation misses out on some of the higher frequency modes, but overall it captures the behavior pretty well. And here's another example for a rod with a tendon held above it at an offset. So pulling on the tendon causes the rod to spring upward, and then releasing the tendon has a very springy falling motion. So it's a very wide field, and there's a lot of designs beyond what I've worked on. So here's an example of a concentric tube robot where you have pre-curved tubes that will take some shape to minimize the stored energy of the opposing curves of the tubes. You also have pneumatic robots like the octarm manipulator here in the center. And then also tendon robots. I'm not sure I can get this video to play. Okay, tendon robots where you very directly bend the robot by exerting forces with tendons. So there's a lot of designs and a lot of cool work by the research community here. So that's a very surface level look. There's some resources here if you want to go further. There's a bit of a barrier to entry since you need a good grip of numerical differential equations to have very accurate control of the robots. But if you want to learn more, the code for the robot I worked on is open sourced on GitHub. And also my PhD advisor, Caleb Rucker, has made a point of publishing our lab's preprints on ResearchGate. So those are freely available without an access wall. And also a shout out to the Soft Robotics Toolkit. It's a very cool resource with a lot of submissions for different compliant parts and robot designs. So one last video here. That was a fun one to make, and we can get into the questions section.
Sounds great. Thank you very much for the presentation, John. We already have one question from YouTube, which is, can you comment on how well these Continuum robots scale? You know, if you wanted to scale one of these to be 50 feet long, what might you need to change in order to make that work?
Well, they scale well between medium and small sizes. If you wanted to make one large, it would definitely scale, but you might need some very big rods. Or you could start looking into more soft robot designs also. That would be easier to get a big robot without having ridiculous materials. But okay. Yeah, the scaling principle definitely applies to the robots.
Okay, can you go into more detail about what sort of material modeling approach you used for the robot?
So there's nonlinear differential equations describing the elastic rods. So that just starts out with the assumption that it's a one-dimensional material. And aside from that assumption, it's an exact formulation of the differential equations, and then we just numerically solve those.
Okay. Also in some of your videos, it seemed like there was a lot of vibration. Are your motors trying to just get the arm in the right position in the steady state, or are you actually actively trying to use these actuators to dampen out the vibrations caused by the materials?
So this is just quasi-static control, where we're just trying to get the motors to move to the right positions. And then they're doing PID control just to hit their individual targets, but there's no system-wide control scheme in place.
Okay. Have you tried applying any learning methods to the control of these arms? Has that worked out any better for you guys? Or is the modeling approach still more appropriate than that?
Our lab has never tried learning methods. There is research on that, but it's not something I'm very familiar with.
Okay. Have you found any practical use cases where this type of arm is the best solution?
Not necessarily. I think the main thing is that it's just a really cool application of applied mathematics. And then at the same time, you have the idea, well, we've got very accurate robot models that have proven themselves to be useful, and we've got very useful compliant tools that are used in medicine all the time. So is there a use case for very accurate models of compliant tools? And I guess the answer to that is possibly. It's still a research topic.
Okay, yeah. Someone from YouTube asks, are there any examples of like large scale, big industrial soft robots that you know of, or?
Yes, Festo has some very cool robots. They're a German automation company. Let's see, I'm not sure if I can just easily share the videos, but I'll post some links to that later.
Yeah, that'd be great if you want to share those in the YouTube chat. I think I've seen those same videos. They've been showing off like kind of animal-esque anthropomorphized stuff that they've been working on.
Yeah, they've got like a elephant trunk and also a parallel arm that kind of looks like ours, but it's a little bit different in the design.
Cool. Yeah, that's great. Someone from YouTube asks, what do you use to justify the research and grant applications?
Well, I mean, there's just value in exploration, in creating new things. You don't necessarily know that something's going to become useful in the future, but some of our best discoveries didn't have just immediate evident value.
Absolutely. Yeah. All right. Well, I think that covers all the questions we received. Thank you very much for your presentation. It was
We actually
awesome.
have one. We actually have one more question that just came up. In the
sure.
chat.
One more.
Sorry.
One last question. Can you recommend any other professors in this field that you think are doing really good work and that we should know about?
Let's see. Well, the concentric tube robot that I showed, it was really championed by Robert Webster and Pierre Dupont. And they've got a lot of good research there. And really a lot of other labs have taken up that torch also. It's kind of cool because of its narrow design, it's really promising for minimally invasive surgery operations. Although I'm no medical expert by any means.
Yeah. Okay. Well, thank you very much. I guess I'm seeing the YouTube stream at a bit of a delay. So if no one sees any other questions, then we will go ahead and move on to our next presenter. John, thank you very much for your time.
Thanks for having me.
Of course. All right. Well, our next presenter, you may know him as the purveyor of marginally clever robots. He's actually also an r/robotics moderator. Please welcome Dan Royer with the Michelangelo Art Robot.
Hi, Michael. Good morning, everyone. It's 8:15 a.m. here, and I'm really thankful that you let me into the showcase. So I'm here to talk today about the Michelangelo Art Robot, which is one of my more enduring successes. I started out making robots 10 years ago, and sorry, I did this talk like a week ago to my local robotics club, and now I'm all stumbling. So I started out with Lego, then Meccano, then I did 8086 computer. That was my first machine. It had a 20 megabyte hard drive. It was tiny. And then about 10 years ago, 11 years ago, I built my first crab robot. I put a link in the chat here. It was a 6-legged walking thing with acrylic parts, and it was pretty hilarious. Nowadays, I make that drawing robot and others like this arm, and someone just mentioned Stewart platforms. So I brought down an old one I have in a library. I got a room full of old robots. I built one of these actually as a dog style robot. So this side would be the face with 2 feet, and then the back has 2 legs as well. And by moving the torso, it walks. Remind me later, maybe I'll make a video about that. Anyways, where are my notes now? So my project, when I first got started in robotics, Arduino wasn't even a thing yet. It was like 6 months away. And I'd read about the RepRap project, and I'd read about 3D printers, and my local hackspace had just started to get one. And the RepRap project was talking about self-assembly, machines that can copy themselves. I thought the printing parts are great, but then you need a machine that puts them together. And I mean, nothing says robot more to me than a robot arm. So I started to design one. And then realized very quickly that there wasn't anything on the internet yet that taught you how to make your own, at least not really, not enough, not a good enough arm to do the job. So I had to teach myself. And I started with 1 stepper motor on an Arduino, and then 2 stepper motor, and quickly realized that robotics is not a cheap hobby. You need some serious cash to get deep into it. So I needed robots that would sell so that I could make some money so I could keep building more robots. I thought, what can I do with 2 motors? And thus the plotter was born. Back here, you can see some examples of pictures that have been done. And I have a Discord where people share their stuff that they make. There's also Elomad Scientist Labs. Big shout out to them. They make the AxiDraw, fellows in plotter making robots. So these are places you can go and see cool stuff. A lot of procedural art intersects with this. A lot of mathematical art intersects with this. And if you're interested, you can see everything from the open source instructions to the open source, like the assembly instructions for the machine. You can see the software project, which is a Java-based OpenGL project that does all of the converting of photographs and generating of, say, fractals into G-code commands. And it's a bit like the slicing program you'd have for your 3D printer. Then there's also the firmware, which is strongly based off of Marlin, which is a firmware that runs in a lot of 3D printers as well, like the Prusas. And if you are big into firmware, if you are an AVR nerd, I would love to talk to you because I have some challenges and I'm looking for talent. Yeah, so that was my main inspiration. Let me take you through very quickly. Here we got one of these machines. Is my cable long enough? It will be. I'll make it long enough. So headphones off so I can reach. There we go. We got a brain board here. We got an LCD panel, and we got 2 motors. And because we know the distance between this motor and this motor as a fixed value, and we know the length of each of these belts, we can do the trigonometry. If you have this distance and you have this distance, you can find the belt length, and you can repeat that anywhere on the wall. So from point A to point B, all you have to know is how much do you turn these motors simultaneously to go in a straight line. Now you repeat that 10,000 times, you get a picture. So sounds easy, but then you get into the nitty gritty of it, and there's some real fun stuff in there. I love puzzles. I love programming. That's why a big part of why I like robotics. It's a real I'm chewing on that nut. I mean, yeah, you know the squirrel from Ice Age? I feel like that when I'm trying to solve a problem. So So yeah, that's me. I've just had a lot of coffee. It shows. And I open the floor. I yield the rest of my time. Ask your questions. Also, if you're interested in any of my other machines, I'd be happy to talk about them.
Hi there. Thank you. I've just put the links that you've given into the YouTube channel as well.
Thank you.
So Dan also, for those who don't know, has been a long-time member of the robotics community, has been a mod in the past.
Honorary mod. I almost never touch anything. Someone reports something, I usually go approved.
But I really, really like this project, and I think it's the art that's produced out of it is amazing, and it's great to see robotics being used in an artistic endeavor, because so often we're seeing just purely function over form and robots built to a purpose, and they are ugly, and whenever we try to make them pretty, we end up going horribly wrong. So to see a robot here being used to do something genuinely beautiful, and I can see that from the posters in the background alone, is fantastic.
Thank you. I would love to make the machine itself more beautiful. People are like, can you put a cover over it? Well, that would be a lot of plastic, and I'm trying to keep my footprint to a minimum. You may have noticed the brain board is overkill. It actually drives up to 6 motors. I'm hoping that every person who's a Michelangelo builder will eventually reuse that board to make one of these, because they will be well on their way. All they got to do is print these parts. This kit is coming. This kit is coming as soon as I can make it happen. Yeah, and of course, like everything else I've done for the last 11 years, it'll be open source. And join us. Think of what we could do together.
Michael, do we have questions from YouTube?
Yes. We just got one that asks, how do you best recommend people share art and robotics? Are there any specific sites, blogs, forums that you use to share your work and collaborate?
Oh goodness, there's so many of them. It can help to start in some place that, let's see. Well, of course, there's art. There's so many subreddits alone, just art, procedural art, plotter art. There's dedicated Discord channels for just about everything. I just got invited to a robot dog channel because I had a hit yesterday on Reddit with some software that I'm trying to simulate. Yeah, but by all means, whether you're into robotics or you're into art or whatever it is, start building your brand now. Blog everything you do, whether it's a success or a failure, because that builds your reputation. And 10 years from now, you'll be thanking younger you, right? Planning ahead is the gift you give yourself. So it doesn't, if you put it on one of those Instagram channels, it's gone in 10 minutes. If you put it on a blog, people can scroll forever and see all the stuff you've been doing. And that really speaks to the volume of work that you've done, and how much you've improved over time.
Great, thank you. We have another question asking, what did you start selling originally, and how did you promote it in the beginning?
I'm actually, I think I'm pretty terrible at marketing. I mean, I love what I do, and I love to talk about it, and I hope that carries through and excites people. But when I started out, I threw up a web page and I put an item there, and it's like, anyone interested? And it was crickets for a long time. But like now, these are in production, right? These are going out soon. It never stops around here. So it scaled slow for me. I never spent money on an influence campaign or marketing no, that's not true. I mean, I made a YouTube video once I thought the machine was pretty smooth. I paid somebody to edit it together. But that's about it. Yeah, I don't need to buy likes. So I'm sorry. I hope that helps.
Oh, it does.
You know what? If you know the secret to, I've never run a Kickstarter because I always thought they were kind of shady, and I never thought I had a product that was so good. If this ever, this is the one I believe in, but if that ever happens, you'll know it. I'll be there. Yeah. So
I would say, and this is not by any means to discourage you from it, but I know that you would certainly not be the first person to suggest a 3D printed robot arm on Kickstarter. So they're definitely
right. And they've been pretty garbage. So
if you wanted to do that, there'd be plenty of people to look at for how to do it right and wrong.
Yeah,
exactly.
Examples there.
My big problem with the Kickstarter is that they say you need a good reason to have the money, like to scale up production. And by the time I get to Kickstarter, I've solved those problems. So then I can't use Kickstarter as a campaign platform. So I don't want to be there and be like, oh, but this could fail, so you might not get anything. Who wants? No.
Yeah. We had another question about the Michelangelo. How many colors can you have in one, print? Can you just swap the colors out whenever you feel like it? What's kind of the, how does that really work?
Tape's coming loose because of the heat in here. So that's
wow.
A CMYK print. That's 4 colors, and you could go more. So because tool changes are not the easiest, it's not automated. I do 1 color at a time, 4 passes, and the software app is set up to handle that change. They recognize, oh, you want to do a color picture, cool, and yes, I won't get into like, oh, it optimizes pathing and does all kinds of sorting algorithms and stop me now. Like I said, too much coffee. Oh, yeah. So
very cool.
As many colors as you like.
Yeah.
It draws, I should mention, it draws up to A2 size comfortably. You can fit A1 size paper in there, where the AxiDraw, much as I love it, their default machine is, I think, A4. So for less money, you get a bigger drawing, but yes. And we're planning, when this batch is sold, I'm going to do a batch of Makelangelo Huge, which is literally like, you see back here, these white hooks on the wall here? So this thing is like 1.5 meters wide and about 2 meters tall. And that's not the hugest huge you can do. So.
I'd just like to chip in. Seeing as we do have a little bit of time here, one person, forgive me if I'm pronouncing this wrong, Ragav, has mentioned, while we're on this topic, if there's engineering students here, there's probably a few art students at your university looking for some robotics talent for making art installations. And that is a great recommendation. Pretty much every university I know, there's artists who are looking for people who can have more talent than them. And by more talent, what they mean is, you mean you can control an RGB LED strip? Wow, we have no idea how to do that. In the same way that, if you if you try to attempt a self-portrait, you'd fall flat on your face. If they attempt to build a robot, they'd have the same experience. So there's a lot of very easy ways that you can get some great publicity for your portfolio if you're trying to go into career. Fantastic opportunities. Art is always meant to be in public display, so it's a great way to get yourself out there as well. And often it is easy things. I know a friend who dressed up a Christmas tree with LEDs and had it, time of music, and he got free entrance to a festival for it. Free entrance, camping, ticket, the works to a festival, just because he had that. And I'm taking, at some point when COVID eventually allows it, I'm taking a robot that I'm working on to a festival, and again, getting free tickets for that. So there are opportunities like that within art that you can absolutely capitalize on at any age.
And art is a lot more freeform than, say, the technical requirements of medical robots or something like that. The Christmas tree, just to learn LEDs, I built a grid with Christmas style string lights and then put them into a laser cut grid and programmed Tetris. And it was fun just figuring out how to build the game of Tetris. But then those lights recycled and wrapped around a Christmas tree. I had the loudest tree on the street. So yes, that was fun. And I was on Make Magazine several years ago. I built like the biggest Jumbotron I could. It covered my garage door. And then they bought it from me at Maker Faire, New York. And apparently it lives in their LA headquarters now. So yeah, that was fun. The guy from the planetarium stopped his car when he saw us filming at night. He had to come over because he's a big fan of light shows.
Yeah, I guess that's the other thing about don't go in expecting to make money, but if you do actually manage to sell something, you'll make a tidy profit from it.
Do it right. Yeah. Don't go over budget. Yeah.
Yeah, that's awesome. That's a really cool experience.
Any more questions from YouTube?
Yeah, we have a few more questions, but we can also just kind of talk. So one other question that we had was from Chris. He asked, you said you like to chew on tough projects. Are there any projects that you've had to spit out and give up on because they turned out to be too hard or too time consuming or anything?
That is a fantastic question. That is a fantastic question. Don't talk with the hand in front of your mouth. What are the deaf people going to do? I'm not, like a bit like a pit bull. I don't know how to let go. That's really tough. Sometimes they become a tomorrow problem. Like I just start with what you know and work from there. There are some projects that I have yet to do, but so like I want to build my crab robot, but using the like a Kubota style, the backhoe you can rent at Home Depot, like a mini sized excavator. I want to take the backhoe part off of 6 of those and build that into a walker and then park that in my garage because I know I can do it. I got to put the money together and get a hydraulics person. And so the problem starts to snowball from there. And I'm like, I got enough on my plate. So problems that oh man, I got to think about that a second because nothing jumps to mind, but I know that there are.
There's one where you've encountered the sunk cost fallacy where you think you've put too much time in it and you should have given up. I've certainly had a couple of those where you realize in hindsight way too much time was committed to something that you should have gone a different route for.
I made a drink mixing robot that was specially designed so that, like, I'd seen a bunch of them where there's a conveyor belt and then a drink, but there was always wiring underneath, and I was concerned that anything dripping is dripping on these electronics, and that's a fire. So I made the platform had 2 belts, so a differential drive, and then it had a scissor lift. So if they worked together, the platform moved this way, and if they worked opposite, the scissor lift would rise and fall, and that's how the drink would touch the things to refill. I did the whole thing with laser cut wood, and it was kind of crappy because it was version 1, and for various reasons, a couple of people were like, "Meh, that's not. Who cares?" So I was like, "Well, okay, fine." There are a few other. I've spent a lot of time building like. The robot back here, this arm, 1,300 parts, so 1,300 unique parts, 300 types of parts. That was a year invested just for this iteration. And I have a warehouse downstairs with enough parts to build 2 more, but nobody's, like one university was interested. It was too complicated. This guy here, 250 parts total. So way, way simpler. That's how I feel like, oh yeah, now I'm on the right track.
Well, that's a good point you make as well. Often in your robotics career, going through school, university, or your career, you can have projects that turn out to be a failure for one reason or another, but the experience of that project is what you then use to succeed in the next project. I've seen someone at university who built a small robot that failed, a bigger robot that was good and then failed, and then a third robot that was absolutely amazing and is going to succeed. The experience, had he not failed those first 2 times, would not have led him to succeeding the 3rd time.
And that's very true. Virtually every robot that I've made has had 3-4 iterations. You ask, when do I stop? Well, because it's how do you define finish? I'll finish version 1 and then just, okay, fusion file to the side, start again with what we got right this time. We can have a long conversation about the business of robots and design of robots. And I mean, yes, thank you for having a coffee break right afterwards because I can keep going. And anytime you like. Michael, Michelangelo is on version 5. Thank you. Sorry, go ahead.
I was going to say we do have a coffee break right after this, but we also did just have a coffee break since Rich ended his presentation a little early. So if y'all are open to it, we can just let you continue until the next presentation starts.
That's really that's very kind of you.
I think it's worth having us at some points. We can go for a few minutes longer, but I think at some point we should stop. So maybe at 5 past instead.
Whenever you're comfortable.
I'll keep an eye on the time. Sounds good. We'll do 5 past.
I wish I could show you here's what I can show you because it's on my computer already. Got to share the screen. This is one of my loves right now is share screen. Where's too many apps? Share screen. There we go. So I started robots, as I said, a long time ago. ROS wasn't a thing yet. A gazebo wasn't a thing yet. This was a hit yesterday on Reddit. And, excuse me, I'm flying blind here. There we go. So this is a simulation of a Spot Mini, and I'm trying to teach it walking routines because I've noticed that a lot of people have dogs, but I haven't seen any great apps for driving them around yet. You know, the few Instagrams I've seen, they hop on the spot, and they might hop while also going forward. Even the famous Boston Dynamics Spot kind of hops all the time. That seems odd. It doesn't seem natural. So I'm trying to work out the path planning algorithm for intelligent foot placement, if you will, to get the behavior that would make sense. And of course, it's open source, and I would love to have smart people who are into animal behaviors come in and figure out how to do this. See here, the feet get too close together, so the center of mass is wrong, and it would fall over in real life. I would love someone who knows something about physics who could simulate this more realistically. I love the idea of ROS and Gazebo, but my understanding is you need to install have a Linux VM set up in order to run those, and that seems like a lot of work. Everybody's got Java. I just want to go.
You should definitely stick around for our session this afternoon for leg robots, if you're interested.
You tell me that I will run the stream and I will be watching it on YouTube for sure. There's my inspiration. There he goes. Yeah.
Well, real quick, we do have a few more questions from YouTube, if you wouldn't mind. We have one question asking, do you have any hardware recommendations for good, low-cost actuators, that are of a reasonable quality?
Cheap, fast, good. Pick two. Right? I don't know your application. This question comes up a lot in robotics. I'm like, okay, what are you trying to do? How much power do you actually need? Now we can start looking around for the right price. Beyond that, I'm sorry, I can't give you more. But if you come to me with something specific, yes, I'll help you out. I love helping out.
Okay.
I'll answer any reasonably formed question.
Sounds good. And then for your projects, do you ever outsource any of the work? Do you ever hire any specialists in certain fields to kind of help you on stuff? Or is it really just you figuring all this stuff out for yourself?
It may look like I've achieved a lot, but that's only because I put in the hours. I'm not very smart. My calculus sucks. I wouldn't know how to do differential equations. Or maybe I have and I don't even know it because I didn't do any university. I'm autodidactic, I think they say it is. So like I went on Fiverr recently and got a guy who made me PCBs, and for $15 he designed a board that PCB assembled, and that was super easy. So yes, I do outsource on occasion, usually because it's R&D. I don't know. I have a hard time guessing how much it's going to cost, but I would, yeah, like I said, I'm looking for AVR people right now, and if they can help me solve my firmware latest thing, I would love to pay someone for that. I'm desperate enough to pay someone for that. Yep. And if there's other talent out there, I'm always happy to connect with them. And then I have references. If someone's like, hey, I need somebody to do this thing, I got your guy for you, or girl, or whatever. I know the somebody. So I always wanted to be that guy. You know the guy who knows a guy? I wanted to be that guy.
Yeah. Well, cool. Thank you very much for your time. That was a great presentation, and we're excited to see where all your projects lead to next.
Well, thank you, Michael, and thank you, everybody else. It's been a pleasure and an honor, and I look forward to doing this again sometime soon. Come and find me on my Discord. Here's a link to it, and I'll see you soon.
Thank you very much. All right. Well, we have reached our scheduled coffee break, so we're going to be on break until 11:45 EDT. So we'll pick back up then, and I'll see everyone in about 10 minutes. All right, hello everyone, and we are back from our coffee break. Our next presenter is going to be Mimico, the biomimicking robot from Thomas. Thomas, if you're ready, go ahead and take it away.
Cool, thank you. Hello everyone. My name's Tom. Where's Thomas? I'll be presenting to you Mimico, the biomimicking robot. If you give me a second, I'll do screen share. I've got a little presentation to show you, and then I've got a bit of a live demo. Cool. So yeah, presentation is going to be short. I'll just go through some background information, just literally just where the idea came from, the idea that I had, a bit more in detail about what it is, how I implemented it, and then the result. So obviously the demo. So I've noticed a lot of the robotic arms that we've got around, whether it's in manufacturing, in dangerous environments, or all forms of robotic arms have some form of controller. All of these are in the form of buttons, joysticks, push rods, all sorts. And all of these can become large, cumbersome, and require a lot of relearning how to move the robotic arm to get to the desired position to go in. This is often really unnatural, and it becomes too confusing for the operators. And basically, I didn't like this. I was told at one point to get more movement out of these robotic arms using these controllers, and it was just too much. So what would be better is human motion. We as humans know how to move our arms. We know how to pick up objects. We know how to extend our arms. We know how to move freely within our environment. What would be a good thing to do is translate this kind of movement into mechanical movement, into our robot arms. I mean, let's consider, the wave. A wave is something pretty straightforward, something that we do every day. From a resting position or any position, we just raise our arm. Raise our arm. Once it's raised, we shake our hand side to side. Pretty simple. But recreating it on an actual robotic arm requires all sorts of calculations, all sorts of predetermined motion planning, and making sure you're not hitting any obstacles. It's just far easier to, just do it, So a few years ago, I had a first go at it back when I was in uni. So this is an old video. Excuse the hair. There was a lot of anyway, it was uni. So what I had there was multiple sensors.
Which uni is that?
Sorry?
Which uni is that?
I went to Plymouth Uni in.
That's the same. I thought so. That's 303. I recognise the room. We went to the same uni. Oh, fantastic! All right.
There we go.
Carry on.
So the video is the video just shows me I've got some sensors on my arm. What that is doing is measuring the angles of my shoulder, the angle of my elbow, and the angle of my wrist. And over on the bench, you can see the single robot arm that is mimicking my movement. Now, what I found when I was doing this was that there was a lot of filtering involved, a lot of noise from the sensors, and it was just very, very inaccurate, and it wasn't working in the way that I wanted it to work. It wasn't smooth. It was just too jittery. So my second implementation uses actually an Xbox Kinect. Now the Xbox Kinect was around for quite a while and was discontinued a few years ago, but it absolutely revolutionized the robotics industry, really. One of the key features that the Xbox Kinect had was what's called skeletal tracking. Now, skeletal tracking is a complicated term for basically tracking a human body. Knowing where each joint of a human body is whilst the user is moving. So I've used this. I've used the Xbox Kinect retrieved this data, this skeletal tracking from the Xbox Kinect, and calculated the angles of my shoulders, my elbows, to replicate the movement of both my left and right arm. And as you can see in the screenshot on the top right, on the left of that screenshot is what essentially the Xbox sees, the Kinect sees, and on the right is what essentially the robot arm should move into. All this data, all the angles, all the joint angles get sent over to a programming board. In this case, I used an Arduino. The Arduino then converts these angles into motor data points and are sent through a customized communications board, which then translates them into the right protocol, the right interface, and sends it over to the actual robot. So I've got a video here, but I think I'm going to be, I'll stop the share. I'll stop sharing my screen, and I'll actually do a bit of a live demo. If I swivel this around. So here is Mimico. As you can see, it's a fairly largish robot. It is entirely made of plastic and wood. So the main body is 3D printed, and this base here, the weighted bit that actually stands on, is just remnants of an old fence post. That is it. So I've got the Xbox Kinect here, and I'll just run the program, and I'll go to show you quickly how it works. So here we have the Xbox is seeing me as I move my arms. The robot follows my movements. I deliberately limited the speed of the motors so that we can actually see the movement and it doesn't knock anything over. I've also added in a feature where if I have my hands open, it stops. It doesn't replicate it. So I have a safety feature to say, stop moving, I'm done. Or stop moving, there's a danger in nearby. Then if I want to retake control, I close my fists and carry on. And stop. That's it, really. That's Mimico. Yeah. Thank you for listening. Thank you for the team for organising this event, and thank you for having me.
Hi, Thomas. I have a question.
Questions.
Hi, Thomas. I have a question.
Hello.
So I love what you built. I love the safety feature with the gripping. So my question is about telepresence. Suppose your robot is in a complete other room, somewhere else on Earth. My experience with telepresence and robots is with a single camera, you have no depth of field. So it's very hard to tell when you're, say, grasping something on the table. How would you approach this problem?
So there's currently there's two kinds of technology at the moment out. There is a stereoscopic vision, which is essentially two cameras that act as two eyes. Our brains are designed to take the images from our eyes, from two eyes, overlay them and calculate the depth of various objects from our eyes. Now the technology exists to actually do that with two cameras. We know the distance between, similarly to the Michelangelo robot we just saw, if you know the distance between the two cameras, you do basic trigonometry, triangulate exactly where the focusing object is, and you can calculate the distance. So that's one piece of technology. The other one is similarly to the Xbox. The Xbox has a depth perception to it. So what you can do is overlay the depth with color, and you fundamentally get a picture with added depth to it. And all of that just gets added to being able to determine where an object is and distance to an object is from the actual camera.
Okay, thank you.
Can I quickly ask what software is this using? Is this being written in ROS or is this done on Windows using the SDK for Kinect?
So this is using the Kinect SDK. I haven't looked at ROS, but I have been working solely with the Kinect SDK integrated into the Microsoft .NET framework. So all the calculations, all the reading from the Xbox, doing the calculations, and then sending them to the controller are all done in C# in the .NET framework. And then it's literally a case of the controller converts those values into values that can be read from the motors.
Okay, wonderful. I'll hand over to Michael, who can give questions from the audience.
Cool. Yeah.
Yeah. So one question from YouTube: is this open source?
This is, I can't remember. It should be. It should be. I can have a look. I'll if it's not open source, I'll make it open source. I'll post up the links to in the YouTube chat.
Okay, great. Another question actually from the Zoom chat. Have you considered combining this kind of approach with a learn by demonstration approach that we see a lot for compliant manipulators or collaborative manipulators?
So I haven't done it myself per se, but the application for it is there. It's half the reason why this kind of robotic movement feels a lot better, a lot safer for various manufacturing environments, especially when so many tools are designed to be used by human hands for use with human movement. It makes a lot more sense to design robots to replicate that movement rather than trying to redesign a robot arm in an unfamiliar environment and try and adapt it and force it to work with tools that were not designed to work with it. So can it be used for learning, relearning, learning and re-executing the same movements? Yes, it can. Is it beneficial? Absolutely, hands down. I would say yeah, do it.
Okay, great. Well, I'm not seeing any other questions from YouTube, and unless anyone has any from Zoom. All right, well, Thomas, thank you very much for your time.
Brilliant. No, thank you very much for having me. Thank you all for listening.
Asking all day if you'd like. If you had to change anything in your design, what would be your next upgrade?
So, yes. Well, I want to do numerous upgrades. One of them is making it wireless. So being able to, at the moment, it's all connected via wire. So I've got countless wires going from one computer to the control board, from the Xbox, so they connect to everything. I do want to make it wireless, and I want to be able to control the robot via, for example, Wi-Fi. So I can have the actual robot somewhere else, and then control it from elsewhere. And that's one step. The other one is to expand the arm so that it's not just the upper arm down to the elbow, it's down to the wrist as well. So I can have movement around the wrist and potentially add a very simple gripper. So I can grab grab various objects and have them move around.
Follow-up question.
Yeah, go on.
It's been pointed out in the showcase that every robot you learn something from every robot you build. So what did you learn from this robot?
Calculations are extremely important and also very complicated. It was one of the things I had to. I spent most time on it, on the calculations, getting the maths right to be able to replicate that movement. So in terms of, I don't want to go into too technical speech, but forward and inverse kinematics, whilst in theory you only need inverse kinematics to get to the angles and then apply them. The forward kinematics also helps in evaluating and simulating where the robot's arm should actually move to. So trying to get that information, simulate it, to test it, to prove that it works before deploying it to the actual robot, required a fair amount of thinking, and that was one of them. The second one,
real quick, so sorry to cut you off.
Sorry.
We do need to move on to the next presenter. But
okay.
Thank you very much for sharing your experience with that.
No, that's good. That's good. Any further questions, then I can put them in the chat, and I'll try and answer them in the chat.
Absolutely, yeah. So he'll be around on the YouTube chat, hopefully, and he'll see those. Thomas, thank you again for your time.
Oh, thank you, guys. Thank you, everyone. Thank you very much. Cheers.
Cheers. And now we're going to move on. Our next presenter is going to be CORO, the collaborative robot avatar, and that is you, Patrick. So go ahead and take it away.
Hello, can you hear me?
Yes, we can hear you.
Great, thank you. Great to be here. I'd like to introduce you to CORO. So this is the collaborative robot that I've been working on for quite some time now, and I'm really happy to share some details about what that process has been like today. So let me try sharing screen. Great. So a little bit about CORO. So CORO was originally created using the Poppy humanoid project's torso and arms. So you can see those similar features there if you're familiar with that robot. He's been 3D printed in thermoplastic, and it gives him enough strength to do small tasks. He's still pretty stable, but the robot itself is quite compliant, which for a small humanoid is actually kind of desirable. Some modifications that were made to the Poppy robot from there were introducing a 3 degree of freedom neck. And on that neck is mounted the Z mini stereo camera. So that serves as CORO's eyes. And then there's the robot and operator computers. So I'm using a Valve Index virtual reality headset, and the controllers and lighthouses, I think those are really good for the kind of resolution that you want in this kind of system. So I think the tracking is really good and stable enough that for this kind of experimentation, it works pretty good, but it's limited to the fact that I have to install the lighthouses in a room. And I'd really like to take CORO to outside and be more mobile. So I'm looking at some other virtual reality headsets to replace the Valve. Also, CORO is made mostly of Dynamixel servos. So for sort of some of the low-level control, I use the Dynamixel Studio for tuning, and also ROS. So we've heard a lot about ROS. I won't go into too much how I use it right now, but I'll share some more details later. And then I'm also using the Robot Claw Robot Claw motor controllers to make an omnidirectional mobile base. And he's just running on a single 12 volt to 14 volt power supply. And to really integrate all the different pieces of CORO, what really came in handy was the OpenVR Hello World app. I started with their open source project and started to integrate all these different pieces into sort of a visual motor integration loop. So that's really where I'm integrating the cameras and just projecting those into a virtual reality headset, taking the motion from that virtual reality headset and using that to move the neck So the cameras will always point where I'm looking. And I do the same for the arms. So I track the virtual reality arm controllers, and I send those commands to robot's arms. That creates a pretty strong sense of immersion. And I want to go into that in a little bit. So I guess maybe one of the big questions might be why? Why would someone build a robot like this? What does this enable you to do? What kind of experiences can you have? Well, first of all, I think it's really fun to do, first of all. So as you can see here, there's something really interesting happens when you create this sense of immersion in, I guess, a physical embodiment that's separate from your own. So the first time this occurred for me, I really was kind of shocked. I was standing behind the robot and I turned around and realized I was staring at myself, but it was doing that from another perspective. So it was kind of different than looking in a mirror. The motions were reversed. So if I moved my arm to the right, the robot moved in the opposite direction. So we weren't quite a mirror image. And so there was kind of a body, just I guess, dislocation. And it really got strong when I was able to look down and see the robot's arms. And when you feel your own arm in the position of an arm that's moving the same way, and you see it moving the same way as yours, you really, really get a strong sense of embodiment and immersion. So I really encourage anyone to try this, and hopefully some parts of this presentation can kind of demonstrate why I think that is relatively easy these days, or much easier than it used to be. So let's see if I can quickly jump back to the video so I can kind of demonstrate some of this. So let's see. Let's stop the screen share. And now, hopefully, sorry, making sure I've got the right video here. Hopefully now we can see that I'm looking down at the robot's arms, and my own arm feels like it's in exactly the same position as that robot arm. So kind of for all intents and purposes, like it's pretty much my arm. If it moves where I think it should move and it feels like it's there, my brain does a really good job of kind of mapping that and creating that illusion that I'm now in the robot's body. So it's quite an interesting dramatic effect. Let me go back to the screen share. Let's see, my presentation stopped. Let's see if I can fix that. There we go. So another thing I wanted to talk about today was to kind of motivate, now that you have a robot like this, what sort of things become possible. One of the primary motivations I had for building a robot like this was to actually explore really good sorts of training data. So by being able to record sort of performance data and pick and place tasks, the idea is that over time could accumulate enough to train machine learning algorithms to be able to do or improve upon the kind of performance that you can normally get just by teleoperating it. So one of the things that I really noticed in doing this is that having a sense of touch provides a lot of guidance towards a good grasp. So when I'm using CORO, I'm actually not able to use that sense. So I rely even more on my ability to see the robot or see what I'm doing. So the hand-eye coordination seems really essential. Let's see, next slide. So let me demonstrate that a little bit. In this example, I'm just playing around with some foam sponges and seeing what I can do to stack them. With the sense of touch, you could imagine you could, really delicately place these objects. In the case of CORO, it's this kind of gross motion. It's a simple pick and place task. So what I'd really like to do is collect enough data of these sorts of operations, those that are successful and those fail, and then use that to see if I could train CORO to do some of these operations for me. So for example, recognize when I'm about to pick something up and be able to complete that task for me. And I think this sort of partial autonomy is going to be really important when the time delays are really significant between the robot and the operator. So one thing that really breaks that sense of immersion I was trying to describe earlier is when you're kind of waiting for the thing that you just commanded the robot to do to become apparent in the headset. So if there's a large time difference between the two, you might take an action and that action isn't instantly reflected in what you see. And so that process of waiting creates, I guess, a lot of operator fatigue is the best way to describe it. So looking at ways that might be able to overcome that. So to share a little bit about some of the learnings, I think there are a lot of things that I discovered in building CORO that I thought are useful to share with the community. Again, to encourage people that this is something that is I think, really been made much more possible in the last few years. And so I found that when I'm moving my arm, it's really an advantage to sort of attenuate the arm motion command. So like taking a quick arm motion or a long distance arm motion should only move the robot arm a tiny little bit. So you can kind of have a precision amplification that way, and that helps with a lot of tasks. Another thing I'm doing is I make it so that the arm or the robot only moves when I press a button on the hand controller. So I'm sort of sending deltas. That makes it easy to kind of rest your arms, and the robot doesn't sort of follow you or smash into things when you're not thinking about it. So it's much easier to kind of control it by pressing the button. Also realize that the higher frame rate over resolution is really critical. So normally in VR and in games, you think the really high resolution has a lot to do with immersion, but actually when live video is coming through the cameras, it seems like the human brain is able to overlay so much on top of that it kind of fills in the gaps on that resolution, and you see reality really well. So it actually means I think it's worth cranking up the frame rate over resolution, because that's when you start to see another way that the kind of sense of immersion breaks. When you move your head quickly or you move the arm quickly, if the camera can't keep up with it, it really kind of affects your sense of immersion. Same thing with depth correspondence. Even 720p per camera, it seemed to be more than enough for sort of triangulation. I'm able to feel like depth works really well when it's close to the robot. It might not be so good further away from the robot, but at least it seems good enough for the types of things that CORO is doing. Also using a gripper button to close the gripper. That's similar to the arm motion. Other things that were important to prototype were the neck kinematics. And so choosing the right orientations and servo positions in that neck was important to move the cameras in the same way that the human's eyes move when the neck rotates or tilts. So experimenting with that also created a deeper sense of immersion.
Patrick,
and I think, yes.
Hate to cut in. We would like to have a few minutes for questions. I'm not sure how many more slides you have, but
sure.
Right, we have so two quick questions from YouTube, where Nate asks, "Are you doing all the kinematic retargeting, or do the hands just move at a constant scaled value relative to your hands? So if you move, 0.1 meters and the arm moves the exact same 0.1 meters."
Yeah, don't quite understand the first option, but if I understand the second one, yeah, it's roughly that. So each servo update, I look at the last position and the present position of the hand that I'm tracking. And that delta X, Y, and Z is what I use to determine the joint angle deltas that need to occur to move the wrist of the arm to that same position. And by attenuation, I just sort of take a fraction of that, or a constant fraction.
Okay, sounds good. And then our other question was, with the VR headset, do you get good enough depth perception to kind of view and manipulate objects?
Yeah, I was hoping to kind of show some of that. So you sort of answering questions at the same time. But the types of object manipulation you can do is I think again kind of limited to the fact that there's no sorts of sense of touch. But you know, I feel like the depth sensing that I am relying on is strong enough that you know, I know when the arm is touching the table. I know when I kind of have the sponge within the gripper. So I'm actually really impressed, even at such a low resolution, what sort of capabilities this off-the-shelf camera is capable of.
All right,
so
thank you very much.
Kind of a lot of failures here, so
yeah,
you know,
absolutely.
still.
Well, great. Unfortunately, we do have to move on to our next presenter, but Patrick, thank you very much. That was, I mean, fascinating and great work.
Appreciate it. Really happy to be here. Thanks for the time.
Of course. Next, we have Joshua Nigh presenting about his powered exoskeletons. Go ahead, Joshua.
All right. Am I live?
Yep, you're live and we can hear you fine.
Okay, let me share the screen. Share. Okay, get out of there. All right, so something a little bit more silly, making a power armor and giant robots using simple circuits. If you're interested in my silliness, you can just look me up on YouTube, Facebook, Instagrams, whatever. And yes, I am distantly related to Bill Nye, so I am a science guy. So just to go over what I'm going to be doing today, I'm going to be talking about some of the background info, how it all works, the project progression, because I didn't just start out making power armor all at once. There was several projects that led up to it, my plans for the future, and taking questions. So it's sort of a BEAM robotics ethos for my projects, where BEAM standing for biology, electronics, aesthetic mechanics, which is sort of the thing where you make a robot using the simplest parts possible, sometimes reusing bits. And the real purpose of this is for entertainment value and popular robotics, because the average person doesn't know what inverse kinematics is or the difference between a sprocket and a gear. So the practicality value, it's kind of low at the moment, but again, it's to inspire people to get into robotics and entertainment. Which brings us to the first project, which is probably the most versatile. Nope. I'm going to be talking about first the basic principles of how it works and into the actual projects. Using basically levers and Bowden cables are our main feature. And Bowden cables are, you know, the little cable that you use to control your bike's brakes and gear shifting. And of course, simple circuits like I have pictured on the slide. I use a lot of double pole, double throw switches that just reverse polarity for motors. And of course, automotive accessories are good because I deal a lot with like car batteries and that sort of thing. They're good for dealing with the voltages and can handle any current spikes you might run into. And for a lot of the prototyping, it's using PVC because it's cheap and really easy to work with, as some decent structural value. And of course, 3D printing, because who doesn't 3D print nowadays? So, next slide. The first project I call the use frame, which is unpowered sports exoskeleton. And I kind of saw these Skeletonics guys with their suit. They were saying they charge like $50,000 for it. I'm like, hey, I think I could probably build that cheaper. So I set about it using PVC and cables. You can see they've got like this weird, wacky lever system for theirs, and they use like square stock aluminum. However, I use PVC and even have gotten around to using metal. And the results are pretty similar. You can see the Bowden cables jiggling around back there, and it's kind of like you can use it as cosplay, really, but it's good for remote manipulation. You can have like little claws or adapt toys or whatever you want, STEM toys to move it around, scare people. And you can see that you got some fairly good accuracy because it's all pretty much like one-to-one mechanical control. There's no motors or anything. It's easy to build, easy to use, and you can dress them up pretty cool to impress people. And naturally, if you really want to, you can start doing like real steel style cosplay fights in the suits. And that would really get people excited, for robotics and stuff. And this is just like the first initial thing, starting to get my hands on working with the materials. The next project that I started is, of course, full-size giant-y fighting robots. These are like 12 feet tall. They're entertainment. They use levers and cables just like the previous one, and they also use motors and actual gas engines on back. I'll pull up a video for those in action. You can see you actually get in them like a science fiction giant robot, and you can see down on the bottom left that snowblower hiding under there because they're really easy to get. And there's also like a drive system all rolled into one. You've got the motor, you've got your transmission, and all you got to really worry about is getting cables and stuff to run up into your cockpit. And you can see these linear actuators, which are sort of these cheap Amazon ones that run off car batteries. They go kind of slow, but it's relatively inexpensive, and the results you get are pretty interesting. And this is sort of trying to capture what Megabots and Karatas were trying to do. They were a few years ago trying to have a giant robot fight, but due to the limitations of like expense and so forth, they made something that a lot of people felt disappointed with. And of course, all these two projects finally led up to making an actual powered exoskeleton using a lot of the similar concepts. It's a double pull, double throw switches like you'd find in any old hardware store, really, put inside of a 3D printed housing, which doing various movements, mimics, sort of allows a robotic suit to run along with you. And since it's all wiring, it's low cost, easy to diagnose. A wire's disconnected, you just go hunting it down. And you can see a lot of use of a PVC in this because, again, it's quick and easy to work with. So I'll just pull up a video of the power armor in action. There we go. You can see you get into the back, kind of like it's like something out of science fiction, the Fallout franchise or whatever. Got a key, using some automotive bits in it because they're really built to be durable, take various voltages, and it's all it seals you up like inside with actuators and stuff, and so you're kind of trapped in there, really. And you can see that there's compound movements are available to the user, depending on how much you're willing to concentrate, because there's kind of janky, so there's a bit of a learning curve to moving around in it. And the thing is with this exoskeleton, it's actually a hybrid unit because the arms are active in that they use electrical linear actuators, and the legs themselves are actually passive, which is just a fancy term for using bungee cords to help support the weight. and it works actually fairly well. I unfortunately haven't been able to do any recorded tests walking around in it, mainly because I've been trying to work on the tension in the knees, because it's all about really finding a sweet spot with tension and that sort of thing. So what's going to be coming up in the future, I'm going to be, as I develop newer stuff, I'm going to be open sourcing some of the older projects. Like I'm working on a handleless power armor controller, where you don't have to grab a hold of it. You just put your hand in there and your fingers are free to manipulate like an arm or a hand or whatever. So I'll be, and also some of the giant robot 3D print files to use to control stuff. And of course, eventually start releasing how-to guides, books, that sort of thing. So to really jumpstart the whole giant robot fight thing, because, you know, people like seeing battle bots and they also want to see giant robots fighting. And of course, entertainment venues, you know, we have giant robots fighting, and even do like rig up some laser tag setup so people can rent it out and, you know, have a giant robot experience that they have a direct link to. And again, this is all like good PR for getting people interested in robotics, in STEM, you know, all that sort of stuff. So I suppose I am ready for the questions, if there are any.
Great. That was fantastic. This is some really cool stuff.
Thank you.
In terms of questions from YouTube, there was one question asked, but I think you kind of immediately answered it on your future plans slide. So yeah, we'll wait a second for any future questions to pop up, or anyone from the Zoom wants to ask some in chat.
Mm-hmm.
I'd like to ask a question, if it's okay.
Go for it.
Right. So this project is obviously very much focused on the mechanical control side of it. I'm guessing there's not use of any. I'm not seeing any sense of any computers or microcontrollers on board, other than what might be used as standard for the pneumatics. Or the hydraulic.
Well, it's actually all electrical actuators. There's no pneumatics in there whatsoever, because you've got to work with a lot of logistics behind that. You got to make sure it doesn't leak and do the hoses and compressors and all that sort of thing. But with electrical linear actuators, you know, you just got to worry about hooking up a wire and you're pretty much done. And it's all switches, so it's not exactly robotics as what an expert would think of it, but it would really, if a layman would look at it, they'd be like, oh yes, that's a robot, even though it technically wouldn't be.
Well, we're being you know, plenty generous with the categorization here, and it's a very much a shifting term. But there's no sensors then on these actuators then.
Well, there are end stop switches. So if the actuator goes too far, you know, it'll prevent itself from overextending and breaking itself. But other than that, it's really about keeping an eye on what you're doing outside, because there's a camera inside the head of like the giant robots and whatever, and so you can kind of see where the arm's going up and down outside. And there's also some indicators, so you know which way the steering wheels are going and how far your torso's rotated. But it's no computers whatsoever, to keep things simple and easy to work with and easy to diagnose.
Yeah, I'm just thinking you might want to consider reaching out to the Reddit Discord community, because there will be some people there who can give you a bit of advice, because you're saying, you know, about the issues you were having with controls swinging the arm. Well, that's something where a very simple sensor and an Arduino can be used to do some of the corrections for things like that. If you're working with just electrical signals, then it might be fairly easy for you to start getting some more advanced control from it.
Mm-hmm. Yeah, it's definitely something I've been considering, but really what I'm trying to do is get the minimum viable product, you know, to get people interested in and show, hey, this is possible without having to invest a whole lot of money or really needing a lot of technical know-how.
Yeah. That's great. We have a few more questions from the Discord. So have you ever tried to lift something heavy that you usually wouldn't be able to pick up with one of the power suits?
I have done some bench tests lifting up a car battery, and those things weigh about 40 pounds, so they're a bit of a pain to schlep.
Cool. Okay. Are there any safety concerns involved in using a full suit? You know, what kind of user protections do you have from the motors and electronics?
Yep, I've been very careful with the suits and stuff, because you've got linear actuators sealing you in, so you got to be careful you don't end up accidentally squishing yourself. So it's a lot of measuring a lot of times, and thankfully these things have end stop switches, so they don't overextend too far theoretically. But I have ruined a couple of them because I run them at about 4 times the rated voltage and they just pop right out. So that is something that can be an issue, but if you keep an eye out, it's not much of a concern. For the large drivable ones, you probably wear a safety helmet and maybe some padding like you would wear when you go rollerblading or whatever.
Okay, great. With that, we are out of time. So, I mean, Joshua,
Okay.
thank you so much. This has been a great
You're welcome.
presentation, and we really appreciate your time.
Yeah, thank you.
Our next presenter is going to be Robotics CoLab. It's going to be Daniel O'Mara. He's going to be talking about building robots to learn robotics. So, Daniel, whenever you're ready, go ahead and take it away. Hello, Daniel, we can't hear you if you're talking.
Here we go. Can you hear me now?
Yes, I can.
Okay, let's see if I can start my video for some reason. There we go. Okay, cool.
We can see. Yep, we can see you.
Yeah, sorry about that. Thanks. I'm Dan O'Mara with Circuit Launch. We are a community of robotics entrepreneurs and a group of people who are really interested in electronics and building businesses all around electronics of any type. This last year during the pandemic, we started Mech Labs, which formerly known as CoLab, is a mechatronics education program. And so we started with the premise that to learn robotics right now, things are advancing so quickly. Like all the projects that are going on here, they blow my mind. And most of this stuff is not being taught in traditional education. This is not like to learn the cutting edge of robotics. You actually have to be building something and learning about it kind of on the go. We realize that knowledge is no longer locked up in the type of organizations and people that it used to be. It's on the internet. Like this is the wonderful thing. Like people can learn to build anything with almost any level of expertise. And so we wanted to create an education program where people can start building robots to learn to build robots, because that's the best way to do it. And so we started this project called Reachy here. And this was we have 3 12-week sessions that actually have been working with this as a platform. So the idea really was to get students of all levels in building stuff, not listening to lecture. We're a 0 lecture kind of program. So we really want to get people in building and learning and growing with an actual platform, an actual robot. So Reachy was a open source project from Pollen Robotics. That actually evolved from, previously you guys saw CORO, but CORO was built off of the Poppy open source robotic platform. And Poppy kind of evolved into Reachy, and now Reachy as a product and a company came from Pollen Robotics, but they are great. They open sourced all of their designs. And so we decided that for our first thing, we were going to jump in, and we were actually the very first group of people outside of Pollen Robotics to build a working Reachy. We have a great relationship with them, and we've open sourced all of our work with this one as well, which you can check out on our wiki at wiki.circuitlaunch.com and be able to actually see all of the process that we went through. And the interesting part that I think is very different from where a lot of other people are in this program is this is all student run. This is all student built. Like we have a technical mentor, but we actually build in, like, all of the students do all of the work. And there was a lot of interesting things. Like, so the Ricci started off with the first cohort where we were really just building the torso, one arm, and the head. And we actually had to take the open source designs, which were all with a much higher end 3D printer, an SLS machine, which uses nylon, is much stronger. You can design things pretty much any way you want without limitations of like the traditional FDM printing. So one of the big challenges they started off with was really just taking those designs and putting it on a regular consumer 3D printer and being able to print this structure. The second cohort was actually, they started working on a concierge robot based off of this. We built the second arm. We put it on a Magni, a Ubiquity Robotics Magni base, and they did mask detection, vocal recognition, and a chatbot program. And actually the robot was able to greet someone as they come in, ask them to put on a mask if they didn't have a mask on. This is back again, still deep in the pandemic. And then be able to actually give them, it's like, hey, would you like to hear a joke, or can I show you the way to the kitchen or the bathroom? And somebody could say, oh, I want to go to the kitchen, or tell me a joke, and Ricci would actually do that. And this is the first jump into ROS for most of the students there, and connecting and putting all of the control systems onto ROS. The third cohort actually went completely into taking Ricci and kind of taking out some of the microcontrollers that were custom to Pollen and only using the Dynamixel Servo SDK and building it fully into ROS and being able to control it all the way through on ROS. And that was a really, really powerful thing. And so they started doing object recognition, orientation, and grasping. And so some really powerful things where we would have them move a block, and the robot would sense that block moved, and then actually go grab it wherever it was and put it back. So that was our third cohort. And so Ricci has kind of evolved as a platform for learning robotics. And the fun part is that whether people wanted to learn CAD design, or whether they wanted to learn deeper into the Python programming or machine learning, machine vision, Ricci has been a really cool platform to kind of teach them that and to go forward on that. So I want to do a quick demo with Ricci. Of course, this is a live demo, and we all know how live demos in robotics are a challenge. So hopefully this works. But to give you a little bit of idea, Ricci, go into some more of the technical side of it. Ricci is a 7-degree freedom arm, 2 of them, and it actually has an Intel NUC for a processor. And then, of course, there are several cameras with lenses, some antenna servos, a neck servo, as a spatial microphone. It can kind of do a whole bunch of things. But one of the cool things I like to demo with this is just a simple trajectory recording. So if I'm going to see how this works now, we're going to go, and we're going to make Ricci wave to everybody. And so Ricci, all I did was go into a Jupyter Notebook, actually, that has running a Python program for the control here, and then simply kept it in, to put it in compliance mode, moved the servos, and now, hopefully, we are going to put it into non-compliant mode. So now the motors are all engaged, and play back our recorded trajectory with Ricci. And then we'll go ahead and put him back in compliance so he's not sitting here with all of his motors. There we go. So now we have that. So that's just a small demonstration of kind of all the fun things that Ricci can do and what we can be able to build. Just to talk about some of the challenges that we had with Ricci as kind of an interesting technical side. The Dynamixel controls were interesting, but we actually found that there wasn't a lot of controllers out that have been published really about using ROS and controlling all the Dynamixels. And we had a lot of problems actually converting it into being able to write it for ROS. The other issue that we found was the original control system, microcontrollers that were working everything through Ricci were little, they are open source, but they were semi-proprietary. We actually had to get them from Pollen to be able to work. And so having that as a kind of a closed firmware was a real challenge for us, because we couldn't find out and figure out why the motors were stalling out or if they were overheating. And there was a lot of issues with some of that stuff. And so it's kind of a testament to open source. It's like we really wanted to push this even further into open source and be like, so let's get rid of some of those microcontrollers, put some of the Dynamixel hardware that we could be able to fully control everything and put it onto ROS, and then have a much better control system. And so that was what our third cohort did. And it was a really powerful thing to really change this to completely open source. Everything is available. We have all of our tips, and unlike a large company, we definitely you can see all of the student writing. So we're not necessarily, it's not a polished wiki or anything like that. So it's fun to be able to go see some of the students' process. And this is we are now offering courses through, or will be opening up a whole bunch more courses to be able to work not only with Ricci, but we have a Boston Dynamics Spot that people just did a boot camp with to be able to do a search and rescue mission. And it's all project based. So we take people of all different levels and get them in learning robotics, which is really what we want. We want to teach mechatronics from a project based method and be able to go from, simple Arduino bots all the way into a lot more advanced robotics using AI and everything else. So I'm going to jump in and just let's see if there are any questions, and then I can talk more about both the program and or Ricci, whatever people are more interested in.
Hi there. I'd like to jump in quickly with a couple of questions. Firstly, I've just spent the last appalling timing. I apologize. I've just spent the last 2 weeks working on Dynamixels for a humanoid robot. So I share your pain there, and I'm definitely going to email you after this as well to talk about some kind of potential collaboration, because I'm also working with the Robotics Society at my university.
Yeah.
When I looked at your original application, we were wondering a little bit skeptical about, how much more work have they done than just reproducing this robot. Completely blown away by the level to which you've improved upon the original design. Going from, one side of 3D printers to another is no mean feat, and the fact that students have taken that on, as well as replacing hardware and getting it fully integrated with ROS, really impressive the way you've really taken the torch and carried it forward. So I just want to say, it's a fantastic project, and I'm going to get in touch to see and find out a bit more about how viable it is for us to try and reproduce it at our university.
Yeah, please.
Okay, thank you. Michael, over to you.
Yeah, so we have a few great questions from the YouTube chat. Nate asks, what recommendations do you have for starting a small business that promotes STEM education and provides a facility and resources for student learning?
Well, I have tons of stuff, but definitely contact me offline and we could be able to talk about that. In general, it's about, for us here at Circuit Launcher, it's all about building a community. Really being able, because it's not the most advanced robotics, it's not the most advanced tools that get people in. It is the other people who are working on cool stuff. So we really just, you can see some of our facility back here with electronics cables and everything. And it's about getting together some people, being able to have a place for them to work and to grow, and then sharing that information. I think the number one problem with hardware and robotics is we're all so isolated. That's why this showcase is so great, is because it can connect us. But if we just keep working on our little silo and we don't get information from other people, talk about our project and talk about their projects, then we're not learning as fast. Like you can learn anything on the internet. What we really need to learn is to have that one person to be able to help you at the right time to get over a hump. And that's kind of the basis of our education program, as well as our success as a community.
Okay, great. Chris asks, what do students need to know already to be able to do a project like this? Or I guess more generally, do you have any recommendations for new students who want to get into robotics for the first time?
Yeah, absolutely. That's we've had students that were very green coming off, done very little in jumping into our team programs and being able to learn where they're at, to all the way to mechanical engineers who I was amazed sometimes couldn't CAD their way out of a paper bag. The thought that someone else knows something so much more than you is kind of a fallacy. Like, there are people who have lots of knowledge, obviously, but knowledge is now accessible to everybody. So the first thing to do is just pick a project that has a technology that you want to learn, and then start building that project. Reachy is very accessible now because we've been able to do this. So I think anybody could jump in and be able to start working on this. And then when you hit a block, that's when you ask for help and come back and be able to catch that. And then, being able to just go from the project that is at your level is the key. So, but beyond that, learn Python is it's one of the major things. Start learning about 3D printing, CAD, whatever is really interesting you the most, because that will lead you to the next thing that you need to learn, much more than what you think you should know to be able to do a project like this.
Great, yeah, thank you. And then one final question is, how do you apply for the programs that you were mentioning that worked with Spot and Reachy?
Sure, yeah. So the easiest thing first is just go to our website, get in touch with us. You can email us at info@circuitlaunch.com. You can go. We have actually our whole education email website is being revamped, so it's not online at the moment. But you can go to the wiki, or just go to circuitlaunch.com and sign up for one of the mailing lists there and get in touch with us.
All right, great. Well, if there are no other questions, yeah. Well, I mean, Daniel, thank you so much for your time. We really appreciate your presentation, and we all learned a lot. So with that wraps up the manipulator portion of the Reddit Robotics Showcase. I hope you all enjoyed it, and we will see you again in a few hours at 2 p.m. Eastern Time for the legged robot portion of our showcase.